So this just represents some plane, three-dimensional space in a vector normal to the plane. Now, if we've got a vector that's not in the plane, and we're going to say that, you know, this is the origin, okay? And that kind of confuses a lot of things, but you understand what I'm showing you. Okay? So now we have a point not in the plane. Okay? So, yeah, let's put the point here just a second, just for the sake of what we're drawing. Okay? So this point is not in the plane, it's actually, if you project it at a perpendicular, it comes down to here. So here's a point in the plane that's as close as you can get to this point, because you go at a perpendicular to get out of the plane to this one. That makes it as close as possible. Now we can prove that and justify it, but right now just accept it. So, you know, this is also perpendicular, orthogonal, whatever that mess means. Okay? Well, if we project this vector onto this vector,
Right.
that means we go at a perpendicular to this vector, and here's the projection. And now let's give this vector a name. Let's call it R, or let's just call it W. Okay? Because it's over there in the space W. So here's the projection onto the normal of the vector W. Okay? And that's just W dot n divided by the magnitude of W times the magnitude of n times W over magnitude of W. Okay? And we know what to do with projections because we saw that very early in the course. Okay? Because it's kind of fundamental. We don't want to have to be struggling with it here. So, remember how to do projection, but I'm sure you probably do. Well, this vector is perpendicular to this one and to the plane, and so is a vector from here to here. Okay? So they have to be equal.
So, yeah, we got actually that part. I think this was the only thing that was throwing us, is that we didn't necessitate that it was coming from the origin.
But when you model three-dimensional space by vectors,
Always comes from
those
the origin.
vectors go from the origin.
Right.
Okay? But when you're modeling points in space
Right.
by vectors,
Okay.
the vectors are, standard position of the vector is its initial point is the origin.
Yeah. Okay.
Otherwise, you don't have a subspace. If this thing doesn't go through the origin and this doesn't, well, this is your, in the context of the least squares problem, this is your image space.
Right.
And this is your null space of your transpose. Okay?
Yeah.
So we know what these spaces are. Okay, so anyhow, this is equal to the projection onto n of W. Well, if we know the projection onto n of W, then this thing here, which is what we're trying to find, see if I want to color code this. Okay. This is what we're trying to find, because now we want to go back into the original space and find where this one came from. And that's going to give us the parameters of our least squares model. Okay? And that's what I'm trying to sort out with this very geometric problem, because once you understand that, then it's just a bunch of symbols. And you just do with the symbols what you would do in a two-dimensional case, or at R2 to R3, okay? Or whatever. You just generalize it, but the symbols are all the same. Okay? And it gives you a guide for understanding that entire development, which I think is one of the capstones that we want to achieve in this course, because you got to understand almost everything to understand this. And I think you guys do. Okay? So here is our, I think I called this W sub R, where R is your
W minus projection of W on that.
row space of A transpose. Okay? So we'll put all that into context. But this is what you're trying to find, and then you find where this comes from. Okay? So, and that's fairly easy, just multiply this by A transpose. Okay?
Yeah. So we were on track.
Yeah.
We were on track.
Yeah, well, the questions
Yeah.
you asked me show me you were on
Yeah.
track. And if you were this far along, that's even
Yeah.
better than I thought when you asked the question.
Yeah.
It sounded like you're in pretty good shape, but you're in real good shape.
Yeah. It was the issue of if it's been perpendicular to the plane, does it necessitate that it's actually coming from the origin like that? And that was our issue. And he said it. You did say it last night that, oh, it's coming from the origin. It touches right there. But, yeah, it was an issue of, okay, this is perpendicular, but it's not within the space. Like, so we were just,
Yeah,
yeah.
yeah, well, let's make the parallels now
Mm-hmm.
with the whole least squares problem, since this has come up and since y'all made really good progress on it. So, yeah, I can do this in the same. Okay, so the parallels with the least squares problem is, I'll go ahead and write this out again. You got your X and your Y. Okay? So you got a bunch of X values, okay? A bunch of X values, and you got your P, Y values, P being the number of data points. I don't want to use N because we so often use that for the dimension of the space. But actually, I'll use M because once you have M of these things, it means that this space here is going to be M dimensional. So this is what it would look like if M was 3, if you had 3 points. Okay? So that this is your Y vector. So your W corresponds to your Y1 through Ym. Okay? And since we're doing a least squares linear model, if it is a linear model, we can do quadratic or cubic or whatever. It just means that the space you're coming from gets bigger. So you got to have more points here. Or more, yeah, you'd have more data points. And if we're visualizing this in R3, okay, then I should have drawn this on the other side since our transformation usually goes that way. But I'm going to have a transformation coming back this way. Okay? So, you know, what's our equation? Our equation is this. And since we've got, if M is bigger than 2, which it has to be if this picture applies, then you can't get a match. A times your C1, C2 is this W vector. Okay? No, A times your C1, C2 is this vector down here. Okay? So this is in your range space, so it is an image of one of these. So this is We don't know what this is, but we know what this is, because this is our Y1 through YM.
Mhm.
Okay?
Right.
Now, if we've got the matrix A, and we find its
Mhm. Orthogonal vector 2A.
yeah, the basis of the null space of the transpose. Okay? And that's what this is. So this is null space of A transpose. Okay? So there we have it. We just have to project this vector on the null space of A transpose, subtract it from this vector,
Mhm.
and then inverse transform this vector, but it's not really an inverse transform because it's not a one-to-one transform. But transform this by the transpose. Okay? So let's see how all that works out. But there's your connection, I think. Let me check my notation.